Started the recording. Okay, welcome. Previously, we discussed architecture design. Now we are considering component level design. So architecture design decides what components will be. Okay, so once we decide on components and their functionality, component level design or detailed design may proceed. Okay. Of course, once you decide a subsystem and break it down to components, the component level design may start. So regarding other subsystems, perhaps you haven't broken them into component level yet. So then these those other subsystems can wait. Okay, so what I'm saying is you don't have to do component level design all at once. That would go against iterative incremental design principles. You are doing that to realize, to implement a certain subsystem. So once you know, you are certain about certain components and their functionality, you may proceed design of those components, while you may be undecided yet about other components. Okay, so in component level design, this is where data structures, algorithms come into play. Okay, so all your skills about data structure design, algorithm design, all this creativity and specialized knowledge go into that. Okay, similarly, interface characteristics, how the component is going to interface with other components, those issues, and communication mechanisms, how the components communicate with each other. So these are to be decided. Who does it? Of course, software engineer. It is important, of course, because component level design determines how efficient each component is going to be. Okay, the steps, we'll talk about the steps once we decide the user stories, for example, or use cases that are going to be implemented by this component, allocated to this component. We can take those as starting points, okay? So let's say you decide that a certain set of features will be implemented by a component, that you may start with the related use cases or user stories and proceed basically from outside in. You start from outside the definition of functionality and you proceed towards inside, that is internal data structures, algorithms, and how to implement the interfaces and so on. So the work product is component design for each component. Okay, but before we proceed any further, what is a component anyway? So I believe we mentioned it in the context of architecture design, but it is nice to see a formal definition Okay, a modular, deployable, and replaceable part of a system that encapsulates implementation and exposes a set of interfaces. So a component is something modular, meaning that its internals are not visible from outside. So a component implements information hiding principles. Deployable. It is directly deployable. It runs. So it is typically in a binary form. And replaceable, meaning that you can replace a component with another one with supporting the same interfaces. Okay, please mute yourselves. And a component encapsulates implementation. Implementation itself is not visible. And the only way to interact with a component is through interfaces. One important point, a component can support multiple interfaces. Okay, and the only way to use a component or for the component to offer its services is by means of interfaces. Okay, so this is a very abstract definition of a component, and you can have specific component models supporting specific component standards. Let's say, consider the Spring framework, for instance. You know, it represents a particular component standard. Or consider, let's say, Java beans, consider ActiveX components, or .NET assemblies. Okay, these are all components with different component models. Okay, so if you have any question, you know, just raise your hand and ask. An object-oriented view is useful. Object-oriented programming, object-oriented design is found useful to implement components. Okay, components are not objects. Well, they are components after all. So objects live inside components, may live inside components. So objects may be used to implement components. Object-oriented programming, therefore, is very useful in that regard. In particular, we use abstract classes to specify component interfaces, and we use normal classes, concrete classes to implement those interfaces as well as in internal business. Okay, as I mentioned, we consider a continuum from, or continuity, proceeding from analysis toward design. So analysis classes give us what is out there in our world that we are operating in our environment. Okay, and then these lead us to So an analysis from an analysis class, we need to move into design. So during analysis, we may recognize that there is a print job. So there is something called a print job. Okay, it includes number of pages, number of sizes, etc., such attributes. And the actions associated with a print job is compute job cost, pass job to printer, send the job to printer. So analysis gives us these class which is not elaborated and which doesn't include any implementation concerns. Okay, so having discovered this analysis class, we may decide that we are going to design a component called print job. It offers two services, compute job and initiate job. So these are services offered by the print job component, and this is the symbolism, graphical element for a component in UML. All right, so then print job component need to be implemented, and so being object-oriented programmers, developers, okay, we elaborate the print job class. Okay, so compute job is a service offered, right? So then it has its interface called the compute job interface class. Interface classes are abstract classes, therefore they don't contain any attributes. They only contain operations. So the other service offered by print job component is initiate job. Okay, then it is represented as an this service is interfaced with this interface class, initiate job. Okay, so it has these methods. Okay, so then you would like to initiate a job as a user of this service. You use these methods, and when you do compute job, computing the cost, you use these methods. The other interface. Okay, so interface classes are, as a rule, abstract classes, meaning that they don't have implementation, but the implementation is offered by a concrete class, so you may provide that through a class derivation mechanism. So the print job class now you see has is quite elaborate. For instance, paper type is we have this paper type attribute in the analysis class, but you elaborate it in terms of paper weight, paper size, paper color in the design class. Okay, in the design class, you see there are concrete functions, operations, which implement these. For instance, compute page cost method is implemented by compute page cost function with the same name in the concrete class. Okay. So the situation here is not very complicated. Once you concretize these interface classes, you are done, it seems. But of course, you may need, as you proceed, some helper classes, and you define them. Okay, it's a matter of object-oriented implementation. Okay, so one thing is that look at in the elaborated design class, number of pages, number of sites. Presumably these are integers. Okay, but how large integers? I mean, are they 8-bit integers, 16-bit integers, 32-bit integers, signed, unsigned? So the type details are not here because these are design classes, all right? I mean, as you implement them, you decide on the representation, data representation, data types for attributes. Similarly, you need to decide on the parameters of the operations, these methods. For instance, compute page cost may need a parameter. I don't know. If it needs a parameter, then during implementation, you decide on that. So you see that there is this design class and the class that is implemented in an object-oriented programming language. So you may imagine that a print job class in, let's say, in C#. So you might think that's not necessary. I mean, why not directly move to the code? Yes, I mean, if the design is simple enough, if it is very clear in your mind what you are going to implement, of course you can do that. Okay, but if the design of the component is tricky, if it is a the algorithms used in it are difficult, okay, and open error prone. So depending on the situation, you may want to take this design step. Okay, so although the types of the attributes are not indicated here, I mean, you are free to do so, okay? There is no law against it. So in complex, in big projects, component level designs need to be documented as designs before the implementation starts, so that you have this perhaps, okay, there is a peer review process to validate these designs, component designs and everything. But if the situation is clear enough, easy enough, you may just proceed to your object-oriented implementation. But in any case, having a component diagram will be helpful, because looking at the component as a graphical element, you can see its interfaces, which is helpful, so that other component designs may rely on these services. Okay. All right, any questions, any worries about? Okay, so let's continue. The traditional view. I don't know what traditional view is. Okay, so control component, problem domain component, infrastructure component. Okay, so what kind of components you might have? Okay, so you may have a component that plays the role of, let's say, conductor, like an orchestra conductor. And some components carry domain, let's say, business logic, as they are called. Okay, problem domain components and infrastructure components. They are sometimes called utility components. They serve utility functions. So there are different ways to identify and allocate functionality to components. Okay, so what you see in this picture is a component diagram. So, okay, so this hierarchical decomposition is to help you to implement the component. Okay, otherwise a component is not hierarchical in nature. That is a component. In the design phase, you may think of the functionality of a component in a hierarchical way, but a component as a software entity is not hierarchical itself. I mean, it has its interface, and you interact with it through the interface, and that's it. So when you read this, interpret such a diagram, okay, so you have a job management system component. So you decompose it into two subcomponents, but then again, this is purely fictional. So you need to handle such features either inside the component implementation or separate components, which are used or invoked by job management system. So this is more like a work breakdown tree, work breakdown structure. Okay, that's somewhat conceptual view. Okay, and the component level design for compute page cost. Compute page cost is one particular, functionality, okay, so one particular feature. Are you going to implement it as a separate component or not? The decision is up to you, okay? So perhaps compute page cost is, you may decide that it be a component by itself, or you may choose to implement it as a function, as a class inside a component. Well, it's your call as designer or developer. But whatever your choice is, okay, you need to decide. Okay, so what are the input parameters? What are the output parameters? What are their types? So, for instance, page size is A, B, C, D, whatever that means. Okay, whatever standard it is. Color is encoded somehow. Okay, so which scheme are you going to use for colors? So this particular implementation is going to use 1, 2, 3, 4 encoding for colors. Well, good luck. Okay, so you see the point. Okay, so when it comes to how to implement a particular functionality, such as compute page cost, you get down to, you need to decide the details, and here is an algorithm. Okay, so this is an algorithm to compute job size given, okay, the attributes here. Okay, so as you see, the design gets very detailed indeed. Again, at this level of detail, you may move directly to source code, or if somebody has to approve this, review this, etc., I mean, from the management, let's say, and you need to document it as such. Okay, so at this, but when this level of detail is decided, I suppose in most cases you may directly write down this stuff in a programming language, object-oriented one at that. Okay, this is what the point of this example is: to proceed in a top-down fashion. Okay, in a top-down fashion from an elaborated analysis model to a model of design that is very close to implementation. So let's say even a novice programmer will be able to implement once when presented such a detailed design. Don't you think? Okay, so this is the mechanics, but there are, how do we go about this? There are some good advice from software gurus. Okay, so we may look into such designs. These design principles are nice to know. So the thing is, I mean, you should be aware of them, but whether the situation, calls for that principle or not, I mean, it is your judgment. Okay, a module or component should be open for extension, but closed for modification. What does that mean? Okay, so extension versus modification, right? What is extension? Extension is about adding new functionality. Okay, so introducing new additional functionality to a component. Okay, modification is modifying the existing code, already written code, and this may result in modification of the services of it. Okay, so the result of the modification can be visible from outside, after all. So modification is somewhat dangerous in that sense, because users of the component will sense it. So you may take care of all the ripple effects. But if you are extending, okay, so you are simply providing an additional functionality, like a new method added to the interface, right? So it won't hurt, okay, it won't break the your clients. Okay, so the users will not be affected. I mean, they happily use the existing methods, right? Okay. Oh, by the way, there is this terminological distinction, although it is not distinguished here. Module and component can be used in different meanings. Okay, so we read the definition of a component, right? A component is a deployment, a unit of deployment, whereas module is essentially a unit of implementation. Okay, so module is something we implement. So the best way, I suppose, to think about them is a module exists as a source code, which is compiled and linked, and it becomes a component, right? And so component is something which is deployed right away. Okay, so when you consider your architecture in a dynamic sense, you should be talking about components. But when you talk about your software product in a static sense, you should be talking about modules. Okay, so there are some, some fine modifications in the terminology. Okay. Okay, what does this principle say? How is it implemented? So you implement a detector component. Okay, it has the interface sensor. Interface provides read, enable, disable, test methods. You see, these are the methods available to users of the detector when they want to use the sensor interface. But anyway, the sensor interface is implemented in different ways, right? Door sensor, smoke sensor, motion detector, heat sensor, carbon dioxide sensor. Okay, so if a new kind of sensor comes along, we are going to add that as the sixth concrete class, right? Derived from sensor class, which is abstract. Okay, so this way, okay, what is going on? We are doing an extension without making a modification. Isn't it nice? So that's open-close principle. So you see, such principles are useful for you to come up with a good object-oriented design in your component implementation. Okay, so there is more actually. If you dig around, you can find more. Liskov substitution principle. Subclasses should be substitutable for their base classes. Okay, so subclass is more specialized. Okay, so base class is more abstract with less methods. Okay, then when you substitute a subclass, that is something more specific. Okay, let's try an example. Suppose your base class is figure and your subclass is circle. Okay, so you may use circle anywhere, figure figure is used. Okay, so that would be Liskov substitution principle, which makes sense, right? So, but the point is, if your code breaks this principle, there is something strange with your code. I mean, how can that happen? So, meaning you play with the base class as if anticipating, as if assuming that it is, let's say, circle. So when you substitute, as if it is square. So when you substitute circle for it, it breaks down. Well, that's bad. Dependency inversion depend on abstractions, do not depend on concretions. So use abstract classes as we used above, and use concrete classes as necessary. So here is a good example. So that your dependencies will be on abstract classes. Okay, interface segregation. Remember, mentioned that a component can support multiple interfaces. So then how do you decide on this multiplicity of interfaces? Well, the principle says many client-specific interfaces are better than one general-purpose interface. Okay, so if the component has let's say, two different classes of clients, users, okay, give each a specialized interface, okay, so that they will be happy and they won't be confused too much. Okay, and of course, our book, as always, gives examples, common closure principle, classes that change together belong together. Yeah, makes sense. Okay, so these principles on surface are saying something that you might think by yourself, frankly. However, it is very easy to forget about these principles and break them in a hurry. So then it is nice to know that there are principles, and if you obey these principles, most likely you'll be doing right. So common reuse principle is somehow repetition of that. So classes that change together belong together. I mean, they must be inside the same component or same larger class. They must be nested in the same big class, perhaps. Okay, so this is a matter of cohesion, matter of fact. Okay, so, and it makes sense if you think about a maintenance situation. So that you handle these in one shot. Okay, so if you look around, I mean, I'm sure you'll find more principles, more guidelines. Okay. Okay, component level design guidelines. So decide on your components, decide on their interfaces, and decide on their dependencies and inheritance. That is, dependencies, a component uses, or can use other components for its services. therefore a dependency arises. So how deep is the dependency chain is an important consideration in determining the complexity of a design. So there are some useful advices here. Okay, cohesion and coupling principles are always important in high level or system level design, as well as component level design. Okay, so cohesion is single-mindedness of a component. That is, a component does one thing and does it well. So it serves one feature, a single feature. It doesn't attempt to serve, provide two different features. Okay, if a component is supporting two different interfaces, they are related somehow. Let's say if you check the printer example above, you see that, I mean, they are both related to print job action, print job service. So they belong together. So cohesion can be functional with layer-wise and communicational. So these are advices for you to how to achieve cohesion. One thing is about the functionality, okay. So component must serve a single functionality. In terms of layers, we can discuss. So the layered architecture. Layered architecture, a layer must be cohesive in the sense that a layer in your architecture provides a particular abstraction to the higher levels. Okay, so in terms of level of abstraction, so a level of abstraction can translate to level of detail, what you are hiding and what you are exposing. In terms of layering, okay, components in the same layer should be consistent in terms of the level of abstraction. So then this gives you cohesion in terms of layers in the architecture. And communication can be communicational. Okay, you can consider communication aspect. So all operations that access the same data are defined within one class, let's say. So you are making one component that deals with a certain, let's say, table in your database. That can be an idea. But remember, these are just rules of thumb to achieve cohesion. Okay, so again, an example of layer cohesion. So control panel layer. Okay, one layer below, there is detector and phone. So detector and phone are at the same layer, meaning they must be in the same level of abstraction in terms of technical details that are hidden inside these components. By the way, you see this drawing uses package, something similar to package notation in UML. So we may guess that these things are not components, but they are layers. So a layer is a collection of modules Okay, so sometimes this layer technology, layer terminology is about modules rather than components, if you are very picky about the terminology. Okay, so phone layer relies on modem layer, which is more specific, as you see, and TCOM, the communication layer, so that a phone is isolated from the communication layer. So this is the beauty of layered architecture. But again, for layered architecture to offer you those benefits, you must care about layer cohesion. That is, each layer providing a consistent abstraction to the higher level, so that a detector and phone are at the same layer for a reason, okay? Not haphazardly put there. Our book gives a set of examples. The related principle is coupling, of course. So cohesion and coupling are discussed usually in the same discussion, in the same discourse. Coupling is the interrelationship between components. Okay, so again, coupling can take place at different levels. Coupling between components, coupling between classes. So if so you look at the component structure, if components are using each other's services, which they should, in a very intricate manner. So when you draw it, you see a spaghetti-like picture, and then you can say that coupling is high. Okay, so if you don't see much edges or much lines in such a picture, then okay, coupling is low. Low coupling means you have easier time in maintenance, in debugging in particular. Okay, so high coupling means difficulty in debugging because an error or an exception will propagate and you'll have hard time tracing it. All right, then there are some good guidelines. Okay, so component design is about, you know what it is about. So how do we go about doing it? Okay, there is, of course, each design activity is essentially iterative, right? So let's look at these steps. Identify all design classes that correspond to the problem domain, okay? Classes that correspond to problem domain are analysis classes. Okay, so you start with those. Identify all design classes that correspond to the infrastructure domain. So infrastructure can be the database infrastructure, communication infrastructure, or services that you are using from external systems. Okay, so it's design your classes or identify them about those issues. Elaborate all design classes that are not required as reusable components. Well, if it is not, some components might be acquired from outside, and let's say commercial off the shelf. Okay, for the others, but for the others, that means for the ones that you are building, elaborate them, that is, provide more detail. This is also called refinement. And message details. A message can be a method call, but if the components are distributed, message can be indeed a message sent over the network. It can be a package, or it can be multiple packages. Okay, so that you see, we are considering all these issues in some order, okay, in an orderly fashion, but keep in mind, be ready to repeat. Okay, OCL, yeah, okay, object constraint language. It is a complementary part of UML, but don't worry about it for the moment. It's a collaboration diagram, by the way. So a production job is a class, but then when you put this column in front of it, well, that means an object of that class. Okay, so you might call this an object diagram because it's all objects. Okay, so production job, work order, job queue, these are objects because they are preceded by this column. Okay, so we might as well call this an object diagram. But anyway, the important point is that this 1, 2, these show the sequence. Okay, so a build job message goes from production job object to work order object. So work order object calls build job method of work order with WO number as parameter. All right, and then the result is returned, and then production job calls the method submit job with the work order number to the job queue. Okay, so submit job then is a method of job queue class. So then you may call that function on the job queue object. Okay, first and second. So that you see in a collaboration diagram, you see the sequence of actions, sequence of messaging, well, similar to a sequence diagram. So a sequence diagram can achieve the same modeling effect. So one can be used for the other in this for this purpose. Okay. And the steps continue. Identify appropriate interfaces. Interfaces might be given beforehand as a part of software requirement specification, but if they are not given that way, then you need to define them yourself, perhaps for internal communication. And elaborate attributes and define data types, data structures. So attributes are decided, but again, we prefer delaying their data types, their representation types, therefore their data types. Okay, so this decision, but must be made somehow. Okay, so make those decisions in step 3C. Okay, refactoring is, as you know, this changing the design or code, most likely, without changing the interfaces or functionality. Describe processing flow within each operation in detail. So how you are processing information, in which order, detail those, decide on these. Describe persistent data structures, persistent data sources, that is databases and files. So perhaps you are not using a database, but you are using the file system directly. That might be the case. I mean, they are persistent data. They live on after your application stops. And identify the classes to manage them. So you worry about the data management aspects. Develop and elaborate behavioral representations for a class or component. If necessary, you may draw state charts for behavioral representation. So if you are into this stimulus response type of situation, is in process control. So you elaborate those behavior. It's the activity diagram. Okay, so let us not go through the activity diagrams. I'm sure you've seen other examples. But the point is that this activity diagram gives you a detailed flow of operations. Again, computing paper cost seems relatively easy. So you may think, okay, I'll just put it in code, and I won't worry about drawing a UML activity diagram. Fine, okay. Sometimes this process is quite involved, and you need to put them in a form like this so that you can discuss it in abstract with others, even with non-technical people. I mean, not non-computer scientists, non-software people, like managers, auditors. Okay, so having this logic as source code may not work well in such situations. But also keep in mind, I mean, this has to be simple because this is a textbook example. Okay, here is the state chart. Okay, building job data, computing job cost, forming job, submitting job. These are the states of some states that a component may go through or an object may go through. So the actions cause state transitions. Okay, so building job data to computing job cost. When does it happen? It happens when data input is completed. Okay, then once the data input is completed, now you may go to computing job costs. So this is state chart notation for UML. Okay, so again, back to building job data. This is our state, our component, or it can be an object as well in a particular state, or it can be a hardware element as well. So when this state is entered, upon entry, read job data. Upon exit, okay, before the state is exited, that is, display job data is done. And as long as the control is in this state, do these steps repeatedly, okay? It is repeatedly check consistency. With some, you know, with some tempo, with some time ticks. Okay, so then you see this state chart formalism gives you a great good handle on specifying stateful components. Okay, sometimes you need that, okay. Again, keep in mind, these are textbook examples and somewhat simple. Again, you might think, okay, I don't need the state chart. I'll just write it down in code. Fine. But remember that this is a simple example. Okay, steps continue. Elaborate the deployment diagrams to provide additional implementation detail. Okay, so deployment, remember, deployment diagrams connect your components with physical resources. Okay, so when you deal with physical resources, such as hardware elements, let's say you are dealing with a sensor on the node that your component is deployed. Suppose you are reading from a camera. Then you need additional detail, for instance, how you are going to interface with the camera. So somehow you need a class that uses the camera driver, right? So assuming that these hardware components come with their drivers, so then we need to implement some interface classes that talk to these drivers, so that the clients or user components will not be bogged down with the details of such vendor-specific drivers, right? So you provide some abstraction, some isolation. So, but then this is where you decide, okay? So, because in this step, we are dealing with physical resources, okay? So think about how you interface them. And refactor every component level design representation and always consider alternatives. Always considering alternatives is a good advice, always. Okay, so even when you write a single line of code or a single loop or whatever, right, every single decision. Is there a better way to do that? Okay, at every level. And refactoring, the purpose of refactoring is, of course, to simplify. Okay, so once you obtain an initial design, it may not be simple enough. Okay, so when you do your first draft, most likely it is more complicated than necessary. So it involves accidental complexity, is this called. Well, you would like to eliminate accidental complexity and only the necessary complexity. Essential complexity must remain in your component design. Okay, how do you do that? Refactor. Refactor your module. Okay, specialized component designs. Okay, so let's say for web applications, for mobile applications. Okay, there are different considerations in designing such component and component-based development. So there was a school of thought in software engineering called component-based development. Now, today, you don't even have to talk about it because it is so well established and so well accepted that, okay, so it is there, okay, so people just do it. So component-based development is the thing. Okay, so then there are some risks that you need to consider and other considerations, how to go about component refactoring, which is necessary to obtain a maintainable design. Okay, of course, as you get down to this level of detail, okay, there are so many things to worry about, so many things to consider. So you need to, again, worry about the domain-specific components, such as domain components specific to web applications or mobile applications or financial applications. You need to be knowledgeable in domain of application, and you must have components that are specific to those domains. All right, any questions? Up to here, we discussed components at some detail. It is detailed design after all. So next is we consider pattern-based designs. Actually, we decided that, okay, object-oriented design is a good way to implement components. Well then, how do we go about that? So object-oriented design patterns give us a great deal of information, okay, how we proceed in our design. So next, we are going to consider pattern-based design. Pattern-based design happens in component level, in architecture level as well. Okay, so we'll be talking about those after the break. Meanwhile, any questions? Is everyone okay? Okay, so pattern-based design is very popular. So people are now inventing, or rather capturing, cataloging patterns for all sorts of things. So why are they so popular? Because a pattern is represents an accumulated wisdom. Okay, so it represents a proven solution to certain class of problems. So people discovered some best practices in time, and then they express these generic solutions as patterns. Okay, so that there is a great deal of activity in capturing, cataloging, design patterns, and for also all sorts of things, okay? Not only for design problems, but also for business-related problems. Okay. But then what concerns us today is design patterns. A design pattern is a three-part rule which expresses a relation between a certain context, a problem, and a solution. Okay, so there is a context in which the problem occurs. Let's say the context in that case is, of course, the component design, or there is a situation, right? And then there is a certain problem within that context. And the pattern provides a solution. So we also specify other aspects of the pattern as well. But a design pattern is something that is abstract. It is expressed as by using UML diagrams and some some comments, some text. Okay. And there is also need to express limitations and constraints. So any pattern will have such constraints. Okay, so then, and I suppose at this point it is best to look into some examples. Here, for that, I'm going to refer to a certain collection of patterns. Okay, so note the address. Okay, so this is the pattern catalog by Creamer at University of Calgary in Canada. Okay, so the design patterns concern basically mostly component level design, and we are doing an object-oriented design, and what we have is an object-oriented programming language to implement these designs. Okay, so historically, I mean, we need to pay our respects to history. Design patterns are collected in a book by 4 authors, Gamma and 3 others. Gamma, Helm, Johnson, and Felicides. So these 4 authors collected object-oriented design patterns in 1995. So it has become so popular. Now it is known as Gang of 4. So these 4 authors are known as Gang of 4, and they refer to their book that way. It's a indeed very popular book. Okay, so the patterns that you see here are from that book. So you see there are 3 classes of patterns: creational, structural, and behavioral. Creational patterns govern creation of objects, obviously. Structural patterns cover aesthetic view, how certain classes are related. Let's say at compile time, basically. And behavioral patterns are more about the dynamical view, and they tell us how objects cooperate at runtime. Okay, let us start with a very simple pattern indeed, very simple creational pattern. Singleton, right? So the context is that ensure that a class only has one instance. So imagine that a class has to be instantiated only once. So how can that happen? For instance, there is this, let's say, manager kind of class that we saw actually in the examples. And then there is, normally one manager, right? So you have one object that belongs to that class. Okay, then need exactly one instance of a class and the well-known access point. Well-known access point is that the user makes that instantiation, but allowed to make it only once. Okay, is extensible by subclassing. Okay, need controlled access, reduced space name, permits refinement of operations and representation, more flexible than static class operators. Well, these are some discussions on what happens when you do that. Let's look at the singleton class. Okay, you have the class name. So you provide these operations. So strangely, operations are at the middle section. But you see they use a static attribute, unique instance, meaning that that attribute, unique instance, being static, belongs to the class. All the objects share it, being static, but then we will have only one object. And data associated with the object, the only object. Okay, then you call the instance, the client is supposed to call the instance method, and then the instance method creates that unique instance and returns a pointer, presumably object pointer or object reference, pointer or reference to that object. Okay, so then the point is, if you by mistake call instance again, you won't get a second instance because the instance will not allow you to do that. So the nice thing about this pattern is, they protect you against obvious errors. Singleton data attribute is, of course, application specific. When you use this pattern, the instead of singleton data, you'll have your own. You'll put your own data, right? Okay, and the unique instance is the object that you create. Okay, so these are for, think of it this way, these patterns allow you to apply, okay, well-known solutions, well-established solutions to problems, and they also prevent the users from making mistakes. Okay, let's pick another one, the factory method. Okay, so what is the point of factory method? Pattern. Define an interface for creating an object, but let subclasses decide which class to instantiate. Factory method lets a class defer instantiation to subclasses. So there are situations where you want users or your clients to create. You limit the options of your clients to create objects. It is important, okay, in any object-oriented development to have 2 points of view. One point of view is the implementer's view, implementers of the class has a point of view, and users of that class has another point of view. Okay, so I keep these two separate. All right, therefore, you don't want your clients to create objects any way they like. Okay, so you want the clients to create objects using your interface. So you see, you are bringing in some discipline. Okay, so for that you provide an abstract class. Okay, so creator is an abstract class and product is an abstract class. Okay, again, keep in mind an abstract class does not have any instances. Okay, so you don't have objects of that class because the class is abstract. Therefore, you need a concrete class. I mean, you need to derive from an abstract class, let's say concrete creator, so that the concrete class does the work, okay? All right, so look at the creator class again. It has factory method. Factory method is abstract. It's an abstract method, meaning that it must be defined in the concrete class. Okay, so factory method is defined in the concrete creator so that it is now executable. Okay, and these other operations like an operation is this called here. It may come with an implementation. No problem with that. The important thing is factory method. Okay, so when your user, okay, calls the factory method. Okay, so the user can call the factory method of the concrete creator. Okay, then the concrete creator creates a concrete product. But the concrete product is a specialization of product which is abstract. So as you let the the point is you don't let a user create a concrete product. It is an object. I mean that will be an object or corresponding to this class, an instance of this class. You don't let users play with or create instances of concrete product or call any method create a concrete product object directly. Okay, they can only create it using the factory method that you provide. So this way, users, must go through your interface. Okay, what are the applicability? What is the applicability? Okay, a class can't anticipate the class of the object it must create. Why say that? A class wants its subclasses to specify the objects it creates and need to delegate responsibility to helper subclasses. Well, Okay, so as you see, it provides hooks. Hooks are interfaces. So concrete creator is a hook for concrete product. Okay, so this is the factory method. So related to that can be abstract factory. So we might as well look into that one as well. An abstract factory. So the client deals with the abstract factory. Now, again, the factory is something that creates objects. Okay, so again, you don't let users create objects of a class directly. And you would like to intervene and have your own interface. So again, it's a provider interface. But then you are creating perhaps multiple objects, but these are interrelated with each other. But this time, the client is when the client code, okay, uses the abstract factory class directly. But you, as the implementer, specialize abstract factory to concrete factory of different kinds. So suppose there are two products, A and B, that can be created. So these product A, product B correspond to objects of this class, objects that different kinds of objects that can be created. Okay, so but then concrete factory 1, concrete factory 2, so you specify special factories. So they being concrete classes, they must implement, provide definitions for, create product A and create product B, because create product A and create product B are abstract, so they must be defined in the concrete class. So then they can be concretized in different ways. The first way or the second way. But then using the first way gives you product B1 and product A1. Using the second way gives you product A2 and product B2. And these products are specializations of abstract product A, abstract product B. So you see this is somewhat more general and more extensive in terms of the objects that you can create. Then the abstract method, factory method class. Okay, let's look at the applicability. Abstract from details of implementation of products, yes, because implementations of products are in concrete classes like product A2, product A1, product B2, product B1, and their abstract classes don't contain implementation details, but the client can only play with the abstract classes. Okay, so the client code refers to abstract classes only. So you see, in a sense, similar to open-close principle. Open-close principle is in effect here, right? Can you see that? You can add concrete factory 3, for instance. Then you don't have to change any existing code. Or you can add create product C, let's say a third kind of product, again, you are not disturbing any existing code. So you see open-close principle in action. So these were, let's look into other kinds of patterns, but any questions up to here? Okay, let's look into some structural patterns. I believe these are quite intuitive, okay? Okay, let's pick perhaps a familiar one. Okay, facade pattern. Well, facade is an architectural term. I mean, in the building sense, anyway. But people, architects talk about facade of a building. So the aim is to provide a unified interface to a set of interfaces. Okay, imagine a system that consists of several subsystems, and these subsystems can have their own interfaces. So each subsystem may provide its own interface. Okay, but then you would like users to deal with a single interface. Facade is that. Okay. So facade defines a higher level interface that makes the subsystems easier to use. Okay, think about let's say a health system. Okay, so it will have many subsystems, as you imagine. Okay, subsystem that deals with, let's say, medicine, some subsystem that deals with examinations, some operations, and so on. It's necessary. It is necessarily built that way because you build it into in terms of subsystems. But then you would like users to use a unified interface. So facade is for that. So that there are benefits, right? So clients will not see subsystem components, I mean, because they will deal with, they don't even see their subsystem interfaces. And it has many benefits. For instance, you may change subsystem interfaces without affecting the facade user interface will be the same. You just have to do the work, and you may the single user interface, which is facade, can live for a long time. And I suppose this is quite an intuitive pattern. Other patterns, let's say, let's pick adapter. This is also supposed to be address a very frequent situation. Okay, sometimes you have a device. Perhaps you use electrical adapters as you travel. If you travel, you know, when you travel foreign countries, you know, sometimes their electricity system uses different voltage levels, right? You need to use an adapter. So adapter pattern is that. It's software equivalent. So you have this adaptee. This is what you have, okay. You have this adaptee interface. not necessarily an interface, an adaptive object. So the users, clients would like to access and use adaptee. However, you would like to provide users a particular interface, which is easy and, let's say, up to the standard. So target is, client sees the target. You see, target is an abstract class. Therefore, adapter is the class that connects the two. You see, this one is using double class derivation, okay, multiple inheritance. Okay, so which is available in C++ quite easily, but sometimes it is confusing, I must admit. But anyway, client doesn't see all this mess, okay? So the client sees the target for interface, okay? And your adapter, okay, here is where you do the mapping, okay? So target request is mapped to adaptee request, and the specific request is this the implementation of this request, okay? So it is specific in the sense that client's request is converted to, understood as, or interpreted as adaptee request. Okay, but if you are using a language that is single, that allows single inheritance, such as Java, okay, adapter inherits from target and uses adaptee method directly. So you see, double inheritance is not a must. Okay, this way, what are the advantages in terms of consequences? This allows you, for example, you may change adaptee. You may try different adaptees, but the user is going to deal with the same interface, right? Because the target abstract class represents some interface that is durable. So you may imagine a scenario like this. Suppose you have in your earlier project, you have an implementation of adaptee class. It is already there, but now in your new project, you would like you can reuse your existing implementation. But in your new project, the client requires a different interface. Okay, so provide that interface as an abstract class. Let the client deal with that. But behind the scene, you are using your existing implementation. So this adapter pattern is a good vehicle for reuse, I believe, right? So let's look into other patterns. What is bridge? Okay, so you see it will look like the adapter pattern. You have, as I mentioned in the adapter pattern, you can change the adaptee, but here it is made into a specific pattern. Okay, you have an abstraction as an abstract class, implementer as an abstract class. And so you can have multiple concrete implementations. So again, remember the open-close principle. And the abstraction also can be refined in different ways. So this allows you to refine abstraction and implementation independently of each other, which is which helps decoupling. Okay, so you reduce decoupling in your system. So as you see, the structural patterns are about how you structure your design, how you structure your classes, so that let's say if your aim is to decouple abstraction and to decouple interface and implementation of a class, then okay, you may go for the bridge pattern. Okay, let's look into some behavioral patterns. Okay, so let's pick one which is well known from data structures, the iterator pattern, collection kind of data structures. Okay, provide a way to access elements of an aggregate object. So an aggregate object can be a collection. Okay, so it can be a list, a dictionary, okay, whatever, right? So a tree, a hash table, whatever it can be, okay. The point is, okay, so the aggregate object is here. It is in concrete aggregate. Let's say it is a list, or it is an array, or whatever. So we don't know what kind of thing it is. All right, so it's an concretization of an aggregate abstract class. So the point is, the client goes through the elements of this aggregate one by one in a predetermined order. Okay, let's say the client would like to walk over a list, first element, and then visit the second element, and then visit the third element, and so on. However, the client must not know the implementation, must not see the implementation of that concrete aggregate. So how the list is implemented, how the dictionary is implemented. The client must not be aware of those issues. So that the client, you see, deals with aggregate as an abstract. So concrete aggregate, the client cannot see. Okay, how does the client do that? The client is an iterator. Iterator is an abstract pointer, okay, to the aggregate. A concrete iterator class is, the concretization of the iterator abstract class. Okay, concrete iterator contains a pointer or reference into the aggregate. However, the client cannot get hold of that pointer. So that the client has no possibility of disturbing the collection or spoiling the collection in any way, or discovering the structure of the collection. All right, so for that, client uses iterator. Iterator has methods, as you see. First, next, is done, current item. First initializes the iterator to the first element in the collection. So whatever the ordering is, okay, so the ordering is known, of course, the iterator knows the ordering of the collection. Okay, next, then takes the pointer to the next element in the collection, to the next object, and so on. So next repeats then. Is done means, when next is not possible anymore, there is no next item, then is done will be true. And you may restart with the first if you like, or whatever, okay? So you have reached the end of the list, end of the dictionary, whatever. You have completed your travel of the tree. Okay, so when this abstract pointer, concrete iterator, it is pointing to some object in the aggregate at any time, you may wonder what that is. So current item method returns that the data value stored in that object, data value that is of interest to you. So suppose you are going through a dictionary, okay, what is the word I am looking at? Okay, so this is the word. So concrete item gives you that. But otherwise, the dictionary, when you say the dictionary, presumably you take the next item in the, whatever the order is there, perhaps lexicographic order, if this is a proper dictionary. But if it is a dictionary in the data structure sense, so the ordering could be anything, right? But again, the client does not know how the ordering is implemented or how it is imposed. Right? So this situation arises quite often whenever we implement a collection type, a collection data abstraction. Okay, so it supports variation in the traversal of an aggregate. Yes, I mean, if you change the concrete iterator, you may change the traversal scheme. For example, you might be traversing in, let's say, increasing order of something. Now you may change. You have another concrete iterator. And now your travel order can be reverse order, okay, so decreasing sequence. So it can be very useful. You see, it takes a lot of explanation, I see, but because we are talking about behavior, okay, so these patterns are behavioral. Okay, let's start. Try another one, observer. How about observer? Okay, one-to-many dependency between objects. Okay, so this situation happens when, the context is when you have data. You have data, let's say, in a database or in a spreadsheet or whatever. Okay, you have some data, and you may want to observe the data. You may want to visualize it in different ways. Right? This happens quite often. Right? Imagine you have an Excel sheet, and you would like a pie chart representation of data, or you would like a histogram. You may want to have different observations on the data. Okay, so then there is this concrete subject is what you are observing, actually, the actual data. Data in your Excel sheet. And concrete observer is, let's say, suppose it is creating the pie chart. Okay, then you might have another observer, which gives you a histogram. Another observer, which gives you another rendition of data. So concrete subject is one, data, and you might have different observations. But the important thing is the subject, the way it goes is observers attach themselves to the subject. Okay, so the subject knows the observer, knows the all observers, so that when set state happens, okay, set state changes the concrete subject. Let's say it's a database update. Okay, so set state can be a database update. When this happens, subject notifies, okay, notifies all the observers. Okay, sends them update. Okay, so calls observers update method. Okay, so when the observers update method is called, the observer knows that the data it is observing, the concrete subject, has changed. So the it must update the visual rendering of the data. So matter of fact, this is one part of model view controller paradigm, right? So this is what happens between model and view. So concrete subject is what we call a model, okay, which contains data. Okay, it can change, okay, so the data is subject to change, but when this happens, the observers should be notified so that they will update themselves. So the view observer represents all the views in abstract, but then concrete observer produces one particular view. Okay, so there might be another concrete observer and so on, so that multiple views to the same model, as it is called, is possible. Okay, so what we don't have is, I guess, the controller, which handles the business logic. You may wonder why model view controller is not here. For one thing, I mean, they don't have, he doesn't list all the patterns in the Gang of Four book. Okay, and model view controller is arguably an architectural pattern. So it might be in here in architectural patterns. Okay, you see how useful they can be, because this situation arises quite often. So the coupling between subject and observer is abstract. That is, we are reducing the coupling. Support for broadcast communication, indeed, because subject is broadcasting to all concrete observers. Unexpected updates can be a significant performance hit. Yes, unfortunately, because if the updates happen very often and you have multiple observers, then you may experience a reduction in your performance, right? Because every time a set state is done, all the observers should be notified, and this could be a real, let's say, overhead on your implementation. So when you read something like a Gang of Four book or any well-written pattern book, they describe in great detail, okay, advantages and disadvantages and the pitfalls, under what circumstances the pattern may perform bad. Okay, all these information you can find in a good catalog. You see, this is just an overview or very summary information. Visitor, well, it's an interesting pattern. Okay, okay, imagine this situation, okay, an operation to be performed on the elements of an object structure. So you have a structure, so the elements of the structure can be of different types or different classes. Visitor lets you define a new operation without changing the classes of the elements on which it operates. So imagine, let's say, a collection consisting of different kinds of elements, and each different kind of element should be treated differently, of course, right? Imagine that you have a collection of animals, and when you visit an animal, there is a particular way that let's say, you pet this animal. So, I mean, petting a tiger would be different from petting a sheep, let's say. Okay, so then this visit must be specialized. Okay, then so you have this abstract visitor class, and each type of, so visitor can mean petting an animal, whatever that animal might be. These concrete visitors can be petting a sheep, petting a lion, whatever, right? So specialized treatment of each type of object. Okay, then these concrete elements have their own implementation, and this visitor visits each element, and as you visit each element, you apply the appropriate action, let's say, accept. Okay, so as you visit concrete element, here is the concrete element, okay. So what are you going to do about it? Okay, so it is given by the concrete visit element A, and this is given by concrete visit concrete element B. Okay, this way you don't change the visitor, the abstract class visitor. As you add new classes of element, let's say as you add a new animal in your zoo, okay, you won't change the visitor class, you will only add a concrete visitor 3. Let's say if you added monkeys, okay. So you see, depending on the situation, these patterns help you a great deal. So there are, the Gang of Four contains, I believe, about 100 patterns. And later on, people extended on those patterns. So there are many more now. And there are anti-patterns too. I mean, it is things that you should not do. I mean, things that are suspicious, okay? Things that easily, patterns that easily lead you to error. So those are anti-patterns. Okay, again, looking at taking a wider perspective, okay, of course, patterns exist other than object-oriented design patterns. So Bushman is a good collection of architectural patterns. So they have a multi-volume catalog of architectural patterns. So the architectural patterns, as you see here, actually we discussed them to some extent last time, but there are much more than that. Let's say model view controller is a very popular architectural pattern when we have situation where there is a graphical user interface and the user has to deal with some data and there is a certain discipline, okay? I mean, there is a certain business logic that the user need to be applying. So it is a pattern about that. So actually we discussed model view part when we discussed observer pattern. There is also controller. Okay. All right, so the model contains data, view deals with the user interface, and controller mediates the transactions and checks, performs integrity checks, and all that. Okay, so you see, it's a well-known pattern for interactive systems. And you have user interaction. Okay, there are also idioms, but idioms are more, they are at a lower level than patterns. Idioms are about how you implement, when you are implementing these patterns in a programming language. Idioms help, okay? So specific, so you might, as you see, these patterns are independent of programming language. They are quite abstract. You can implement these patterns in any object-oriented programming language, matter of fact. Okay, then specific to the language, people also invented and proposed idioms. Idioms are programming language specific. So you may look into the literature for that. So the point is, whatever you are doing, when you are in a design process, okay, it is best to be knowledgeable about existing patterns. Okay, people invented patterns for workflows, patterns for whatever, right? Patterns for smart contracts, everything. So whenever there is some accumulated knowledge, there are patterns. Okay, any questions? We only scratched the surface. I mean, There are large collections and catalogs of patterns you may find. So the more knowledgeable, the more patterns you know, the better equipped you will be as you tackle design challenges, right? Okay, guys, any questions, anything that concerns you? Okay, so let this be the end of our discussion this evening.